Yeah.
So the harder part is if x is an accumulation point of this sequence, then x must be a subsequential limit. Okay. So let me give the proof. Okay. And one way to prove it is like this. You'd say, well, let's first observe that x, an accumulation point of some set, implies that every punctured neighborhood actually contains infinitely many elements of S. Right, it's not, the definition of a cluster point says every neighborhood, every punctured epsilon neighborhood is going to contain one element of S, right? But that actually forces it to have infinitely many elements of S, right? Because you think like this, here's my X, and I choose some epsilon neighborhood. Okay, choose some epsilon neighborhood. You know, since this is a punctured neighborhood, that there's some element of S in there, right? Okay, but then you take a new epsilon. Take this as your epsilon. So I'll call this epsilon 1 or epsilon 0. No, let me call this epsilon 1. Okay. You know that in this neighborhood, there's an element of S. In this punctured neighborhood, there's an element of S, right? Let's call that guy S2. Right? It's not going to be S1 because S1 is not contained in there, right? This is an open disk, right? S1 is on the boundary of that disk. So you know there's some S2 in there, right? And so on and so forth, right? So inductively, you can show that, for any number n, there are n elements in there. Okay. Yeah, all right.
Can we just use that now going forward, like for future proofs, we can say that any cluster point has infinitely many?
Yeah. Okay, so this is the idea, right? You'd have to write this down more precisely, but you see how the proof would go, right? You'd say, well, given any epsilon, I know that there's one guy in there, but then I know that I can find a point closer than that guy, and I can find a point closer than that guy, and so on and so forth. Right? So there's you can make a sequence. Right? You can make a sequence. Right. So yeah. Okay. Okay. Yeah.
That's kind of where I had my question. So do we have to construct an NK when we're making subsequences?
Yes. So let me show you how. So we're not done yet.
Okay.
We're not done yet. So I'm just proving this observation.
Yeah.
Okay. Okay. Yeah. We need to be a little bit careful. That's why this backwards direction is the hard one. Okay. Okay. So we have this fact. Okay. Any accumulation point, any punctured neighborhood is going to contain infinitely many elements of S. Okay. So now we know that X is an accumulation point of Xn. Right. And we want to show that there exists a subsequence, xnk, such that xnk converges to X. Okay. So the first thing you do is you say, well, let epsilon sub n be 1 over n. So we're going to take a sequence of epsilon neighborhoods. Okay, and their radii are going to be decreasing, right? The first, here's our x, right? Epsilon 1 is 1, epsilon 2 is a half, epsilon 3 is a third, etc., etc. Okay, right? Then, right, since x is an accumulation point, we know there exists some element of xn in this punctured epsilon 1 neighborhood. Right? Right? Call, right? Take that element as our initial, as x of n1, right? Right, so let n1 be the index of that element. Okay. So there's some guy in here, maybe it's x sub 100. Okay. We're going to call that guy x sub n1. Okay. So 100 is our n1. Okay. Now, so yeah, you can do this inductively. I'm just going to show you how you get the next guy. Okay, so for epsilon 2 equals 1/2, we know that there exists infinitely many elements of x of n in n x1x n e2x. Right? So there's infinitely many guys inside here from our set. Okay. Choose one whose index exceeds n1. Right? Because we want our subsequence to have increasing indices, right? We don't want to be like x100, x3, right? x3 may be inside here, but we don't want that guy. Fortunately, there's infinitely many of them, and so we know that somebody's going to be bigger than n1, right? That's why we need this infinitely many, right? There's infinitely many guys inside there. Well, I'm pretty sure that, I'm guaranteed that somebody's going to be more than 100, right? Right. So
because there's finitely many under.
Yeah, exactly. Right. Right. So choose one whose index exceeds n2. Let n2 denote that the index of that element. Right. So you get, maybe x1000. And 1000 would be your n2. Excuse me. Yes, Nick.
Guys, just to clarify, do we need to say the reason that we know there's going to be another n larger is because we have finitely many beforehand? Or is it the fact that it's infinitely many, so of course there's going to be another?
It's the latter, right? There's infinitely many of them, so you know that you're going to have one whose index exceeds n1.
Well, like in theory, we could say that there were infinitely many beforehand, but there's still going to be another one.
No. What do you mean before what? Before?
Well, not in this case, but I'm just saying.
Before n1?
No, sorry. Ignore that.
Okay. So you see how we're going to construct the sequence, right? So in the end, we obtain sequence of x of nk where the nk are increasing, right? And the distance of x of nk to x is smaller than 1 over k.
Is that because we were just making our n basically?
Because you see how we took n1 was in the epsilon 1 neighborhood, right? Epsilon 1 was 1. N2, xn2, excuse me, was in the epsilon 2 neighborhood. Epsilon 2 was 1/2, right? And so on and so forth. So we constructed so that x and k is in the epsilon k neighborhood of x, right? So that means that the distance is smaller than 1 over k. Okay, so that's our subsequence, right? X of nk converges to x, right? So x is a subsequential limit. Of the xn. Okay. Any questions? Yeah, Arya.
Can I actually ask a question about the other direction?
Yeah, sure.
Where we claim that if
It's a subsequential limit, then
it's got to be an accumulation.
yeah, sure.
So the example where you have -1 to the n,
Yeah.
you have 1 as a subsequential limit, but 1 is not an accumulation point, right?
Oh, you are right. X is an accumulation point. That's right. So what? Maybe I'm sorry. I guess that side is wrong.
I guess.
I guess
Could you say like if it's not a constant?
if so, yeah, you'd have to say that x. If x is an accumulation point of xn. That is not one of the xn, right? But let me think of how to make that right, because it could be that I'm getting mixed up between accumulation. There may be some distinction between accumulation point and cluster point. It may be that for cluster point. Let me look it up, because I'm sorry. This is exactly why Hitler, was angry. In the movie. Okay, yeah, you were right, Arya. Thank you. Okay. In any case, this is the part that this part here is what we're going to need today. So, okay, what can we do? I'm not sure if we can do both parts of. So let's. Okay, so let's finish up Bolzano Weierstrass. Okay, so I told you that there are two kinds of Bolzano Weierstrass theorem. There's one for sets and one for sequences. Right. Okay. So the first. Right, so we had one Bolzano Weierstrass theorem, Bolzano Weierstrass for sets. Once I was at a party with a bunch of mathematicians, and somebody said to me, so who is the greatest analyst in the late 19th century? And I was like, I didn't want to make any guess for fear of being ridiculed. But instead I was ridiculed for not having an answer. Like the mathematician, I was like a kind of senior guy, he turned to his friend and he said, this guy doesn't know who the greatest analyst in the 19th century is. And I said, well, okay, so who is it? And he said, Weierstrass, of course. It's like, okay, yeah, all right. Anyway, you see.
Bolzano.
What?
Fort Bolzano.
Well, anyway, you see how
Well,
what kind of
someone's name
pull?
was first. That's all I get.
No, I mean, it's true, Weierstrass is, that's probably the right answer. But you see what kind of poor social skills mathematicians have. Yeah. So yeah, it was like my first job or something. I was invited to a party. Yeah. Okay, so Bolzano Weierstrass for sets, you remember, is that if your set is bounded, right, if S is bounded and infinite, right, in R, right, so you have S is a subset of R and it's bounded and infinite, then it's guaranteed to have an accumulation point. S has an accumulation point. Okay, and we use this, we use Bolzano Weierstrass to get the completeness of R, right? That Cauchy-ness implies convergence. Okay, and I still haven't given you the direct proof. I had you all do the proof by contradiction, but I promised that I'd give the direct proof. And if there's time today, I'll do it. What is it, Nick?
Doesn't this run into the same kind of problem that I brought up just before?
No, because it's an infinite set. It's an infinite set.
Oh,
So there's different values, right?
Okay.
You can't have like
Yeah.
this as a set. It's infinite.
Yep.
Okay. Then there's the second part, Bolzano Weierstrass for sequences. Okay, so A sub n, a sequence of real numbers. If your sequence is bounded, then A sub n has a convergent subsequence. Okay. Any bounded sequence has a convergent subsequence. Okay. So the proof of this is actually pretty straightforward. You say, well, let S be the set of all values. Okay, right? The set of all values of your sequence, right? So if they're all 1, this set has 1 point. Okay, right? If it's the sequence -1, 1, -1, 1, blah blah blah, this guy will have 2 points in it. Okay, so it's a set of all values. Case 1, suppose that the set is finite. Okay, suppose the set is finite. Well, then you've got it easy, right? You definitely have a convergent subsequence. And think like this. Suppose your set had suppose S consisted of 1 value, right? well then you'd have a convergent subsequence, right? Your set would be, your sequence would be constant, right? Okay, now suppose, let's say you have two values. Suppose you have two values. Do you have a convergent subsequence? Absolutely, right? Because, you know, one or the other value must have been hit infinitely many times, right? Choose the one that's hit infinitely many times. That's your subsequence that converges. That's your subsequence, it's constant. Okay, you'd have a constant subsequence, right? You know, maybe you've got a sequence that goes -1, -1, 1, 1, 1, 1, 1, 1, 1. Well, just choose the one that has infinite, that is hit infinitely many times, and use those indices as your subsequence, right? Then you've got a convergent subsequence. It's constant, so it's convergent, right? Okay, so that's the idea, right? So you say, well, look, there is some S in S such that A sub n equals S for infinitely many values of n, right? Right? By the pigeonhole principle, if you want to use that term. Right. If there's only 3 values and you've got infinitely many pigeons, well, one of these pigeonholes must have infinitely many pigeons in it, right? So choose that guy, and then the indices will. Yes.
Can I just clarify? The statement of the theorem is so it has at least one convergent subsequence.
Yeah. So I mean, in mathematics, I'm afraid that's how you say it.
Yeah.
You say A has a convergent subsequence, right? It may have 2, it may have 3.
So we're not claiming that any subsequence is convergent.
No. A sub n has a convergent subsequence.
Thank
That's
you.
it. Yeah. So it's funny in mathematics, you know, we're not saying it's that there's only one, right? What we're saying is that there is one. There may be 2, there may be 10, but even if there's 10, there's certainly one, right? So that's just how mathematicians talk. Okay. So there are infinitely many values of n for which A sub n equals S. So let's say that they are n1, n2, n3, etc., where the n(i) are increasing. Right? Then A sub nk is constant, is a constant sequence, constant subsequence, right? Converging to S. Right? So yeah, we definitely have a convergent subsequence. If the set of values is finite, you kind of easily get a convergent subsequence. Yes, sorry, go ahead.
Did we just, when you say n1, n2, n3, do we just like pull that?
There are infinitely many indices. Let's call them n1, n2, n3, blah, 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 right? And we can assume that they're increasing, right? We don't have to put them, we can take them in increasing order. Maybe I should say call them. Is that better? Call them. Let's call them n1, n2. Okay. Case 2. S is infinite. Infinite. Okay. I'm not seeming to be able to write infinite. So if S is infinite, right? We also know that S is bounded, since S is also bounded, right? Because the sequence was bounded. We know that S has an accumulation point. Right? Right? But by the problem that we just showed on the board, right? But as we just showed, then there exists a subsequence A sub nk that converges to that accumulation point. Right? So we've found a convergent subsequence. Right? Because we just showed that if a sequence has an accumulation point, then there's a subsequence converging to that point. So the homework problem actually is the main part of this Bolzano Weierstrass theorem for sequences.
For sequences.
For sequences, yeah. So this is the Bolzano Weierstrass for sets. This is Bolzano Weierstrass for sequences. There used to be a method of teaching where the professor would never prove anything, but would simply give the definitions of things. It's called the Moore method, M-O-O-R-E, after the Texan mathematician who popularized it. So there would be no textbook, there'd be no nothing, but I'd give you definitions, and then I'd give you small problems, right? And you prove them, and just prove them, and keep on going, and you basically prove all the material in the course. That's a little bit what we're doing here. I think it was recognized as a pretty effective method, but it can only be done with a small group. Yeah, so we're not doing that in its full-blown glory, but we're sort of doing that here. Okay, so let me hand back the exams. Exam scores ranged from really good to not so good. If you're on the not so good end, then I hope you'll come to. I don't want to look at anybody, so let me say, like, I think everybody should be able to do this. So come to office hours, and I'll try and clear things up. Okay. So don't give up, and just keep on trying. When I first started doing theoretical math, I was really discouraged because I didn't understand anything. And so I went to my professor, Professor Wiles of Fermat's last theorem fame, right? The guy who proved Fermat's last theorem. He hadn't proven it at that point, but he was famous guy. I went to him and I said, Professor Wiles, I just don't understand anything. And he said, don't be discouraged. He said, don't be discouraged. When I first picked up a theoretical textbook, I did not understand it at all. And that was enough. That's all he said. But I kept on going, and then became a math major eventually. And then another maybe encouraging story, I don't know, is when I was in my second or third year of graduate school, I went to my advisor and I said, Professor Pepperman, I'm sorry, I don't understand anything. I just feel stupid all the time. And he said, welcome to mathematics. He said, if you're actually doing mathematics, you're going to feel stupid 99% of the time. Right? So yeah. Okay, so yeah, come to office hours if you're if things are confusing.